So we're going to be looking at logarithmic differentiation. I'll make sure I say that correctly because it's a bit hard to pronounce sometimes. And this is useful when we want to try to find the derivative where the variable is the exponent. So two examples of this are if we had the equation y equals 5 to the x, and if we had y equals x to the x. So how do we solve these? We can't use the power rule because our variable is the exponent. So how do we solve these? And we do this by rearranging the equation and manipulating it using logarithms. So what logarithms do is they help us essentially get rid of exponents. So if I say I had some number b and I have it raised to some exponent c, and that equals some number a, I can rearrange this in a logarithm to say the logarithm of base b of a is equal to c. So this helps me too in terms of solving things because, and the reason why we love this for derivatives is a really well-known derivative is the natural log of x. The derivative of the natural log of x, so dx of the natural log of x is 1 over x. So this is a really well-known derivative, and using this we can manipulate our functions to make them easier to solve. Now you might be saying, well, this is natural log, this is log. Natural log is all the natural log is a log to the base e, which is Euler's number, which is something like 2.718 repeating. And so if I have the log of base e to some x, that's the same as saying I have the natural log of x. Okay, so these two things are equivalent. So let's use these principles to solve this first one right here. So we have y equals 5 to the x. And the first thing I'm going to do, before I even take the derivative, is I'm going to take the natural log of both sides. And I can do that, algebra principle state, so long as I do the same thing to both sides of the equation, it stays equivalent. So what I do to one side, I have to do to the other. So on the left side, it becomes the natural log of y. And on the right-hand side, it becomes the natural log of 5 to the x. And another property for natural logs is the same thing. It allows me to take this exponent out and actually bring it down here to be multiplied. So this is the same as saying I have x times the natural log of 5. These two things are equivalent. And this allows me now to make it a lot easier to solve because now I no longer have my variable in the exponent. So what I'm going to do now is I'm going to take the derivative of both sides. So dx of the natural log of y is equal to dx of x times the natural log of 5. Now on the left-hand side, what we're doing here is we're actually doing a partial derivative. So we are going to differentiate the natural log of y. So the way we take into account that we're doing a partial derivative is because I'm differentiating y, and it's the same derivative. If the derivative of the natural log of x is 1 over x, then the derivative of the natural log of y is 1 over y. So this becomes 1 over y, and in order to account for that partial differentiation, I'm going to write dy dx. So I'm keeping track that it was a partial derivative. And then on the right-hand side, I just have the x variable. This natural log of 5 is actually a constant, so I can pull it out. I'm not differentiating it. And the derivative of x is just 1. So it ends up being the natural log of 5 times 1. Now you might be saying this does not look simple. How is this easier? We're going to break it down here. So first thing I'm going to do is I'm going to rewrite dy dx. Because all dy dx means is y prime. Or f prime, depending on which variable you're using. But this is just another way to say the derivative. That's it. So these two things are equivalent. So I'm going to even just write that down here so we don't forget. dy dx is equal to y prime, which is also equal to f prime. They're just the same thing. You can literally think of it like a variable. So I'm going to rewrite that and get rid of it. So that's saying I have y prime times 1 over y is equal to the natural log of 5. Now I want to move this y to the other side. So I have y prime equals, I'm just going to bring it to the front. So this y times the natural log of 5. Now I don't want the y variable. I want all my variables to be in terms of x. So how do I undo that? If I remember way back at the beginning, y is equal to 5x. So I'm just going to substitute that in for y. So y prime is equal to 5 to the x times the natural log of 5. And this is the derivative. We're done. So now let's take a look at if y equals x to the x. We're actually going to follow the same steps. So we have y equals x to the x. We're going to take the natural log of both sides. I have the natural log of y equaling the natural log of x to the x, which allows me to bring down that exponent. So that's the natural log of y is equal to x times the natural log of x. Now I'm going to take the derivative of each side. So d dx, d dx. So again, the left-hand side stays the same, and the great thing about this method is the left-hand side follows the exact same pattern every time. So taking the partial derivative, we take into account by saying dy dx is equal to 1 over y, and that is equal to this d dx of x times the natural log of x. So I have two x's here that I have to take into account. So what I'm going to do is I'm going to use the product rule. If you're unfamiliar with the product rule states if I want to find the derivative y prime, actually, let me rephrase it like this. So if I have some equation y equals f times g, then the derivative y prime is going to be the derivative of the first times the function of the second plus the function of the first times the derivative of the second. So the way I like to do this is I always like to define my variables to start. So f prime, and g prime. So my f is going to be represented by x. That'll be my first one. And the order doesn't actually really matter, but I just like to go in logical order. And so f prime, I just look at what is the derivative of x. Well, that's just 1. That's not too bad. And then my g's would be my second function there, so that's the natural log of x. And the derivative of the natural log of x, we've stated, is 1 over x. So now I have each of these variables. I can just plug them in. So I have dy dx times 1 over y equaling, all right, so my f prime times g, which is just 1 times the natural log of x, so 1 times the natural log of x, plus my f, which is x, times g prime, which is 1 over x. So I'm going to rewrite this, and I'm going to rewrite the dy dx, I'm going to write as y prime, just to get rid of that. So y prime times 1 over y is equal to 1 times natural log of x, just natural log of x. And then these x's cancel, so x times 1 over x is just 1. So just plus 1. I'm going to do the same thing I did before, so I'm going to multiply this y to the other side. So y prime equals the natural log of x plus 1 times y, and then I look back to, I want to get rid of this y variable, so I want to do a substitution for y, so I look back to the original function that y was just equal to x raised to the x. So y prime is, and I'm going to put it in the front because it looks nicer, x to the x times the natural log of x plus 1. And this is the derivative of y equals x to the x.